And introduction. Give me 1 second here. Zoom just decided to interrupt for one moment to tell me this is being recorded, and that's just fine. So thanks for that kind introduction. I had no idea I had over 100 papers published and 4,000 citations. Oh my goodness. It is an honor to be here today. And I thank everybody for attending. I especially thank some of my colleagues from Alberta for attending. It is 5 in the morning over here, so I appreciate their dedication. So today's talk is going to be technical, but it's also going to be a little bit societal as well, because I've included some of the slides that we use to teach children in local schools about solar energy and solar fuels and climate change as well. So I hope to cover a wide range of topics today and a little bit for everybody who's attending. So let me begin with something that I hope we're all aware of. I'm sure we are. And the motivation for this research is, in my opinion, one of the biggest problems we are facing today is climate change caused by emissions of carbon dioxide and also methane. And the UN put together an intergovernmental panel on climate change. This slide is already a little old in the amount of CO2 in the atmosphere and whether or not we can limit the increase in temperatures that we're going to all be facing in the coming years. But in my opinion, and I think it's basically fact that it's undeniable that human emissions through industry and various other activities is changing the climate, is causing everything to warm up. And I think it's very urgent that we do something to reduce these emissions. This slide says dramatic cuts are required to limit the temperature change to 1.5 degrees. A lot of folks I talk to say that we're not going to make it to 1.5. It's going to be higher before we finally cut back on our emissions. There's all kinds of reasons for this. There's lags in how fast the climate can respond. There's lags in how fast we are going to stop emissions. I don't think we are. We are still, in fact, increasing the amount of CO2 that we're pumping into the atmosphere. On top of a mountain in Hawaii is a CO2 measuring system. You can access that website at any time, and you can see that you have seasonal differences in the baseline, but we are not decreasing the amount of CO2. And this graph doesn't include methane, which is another powerful greenhouse gas. And I think we all have to come together to stop this. And so we're doing what we can in terms of research, in terms of training people, young people in the labs. The young folks are the ones who are going to inherit this problem. Okay, don't thank us, older people. And also, we also do a lot of public and student outreach in schools. Okay, so there are, of course, many ways to address this problem. There won't be one solution. It's going to be a solution of many. It's going to be climate change. We're going to change it with 1,000 cuts. One of them will be wind and hydro production. These pictures are from Alberta, by the way. I was on a vacation recently, and this is near Pincer Creek, Alberta, in the southern parts of the province here. There's an awful lot of wind, and so we have a lot of wind generators down there. There are some dams as well for hydroelectric, but I think the point I'm making with this slide is to have enough wind to produce electricity, or obviously hydro, it's location dependent. We don't have windmills everywhere here because it just doesn't make any economic sense, and it doesn't produce enough electricity. Obviously, you can't have too many dams in the prairies or the desert and those sorts of things. So these are intermittent and dependent on location. Solar energy, of course, is the way we're going to go. Ultimately, everything is solar powered anyways. And I think it's absolutely true that wind, well, the wind doesn't blow all the time and the sun doesn't shine all the time. So you must store this energy if we are going to use renewable sources. It is inescapable. And so we are working on ways to store the energy using carbon dioxide and ultimately nitrogen as the storage medium. So one of the ways that we can envision developing a system to address the problem is we can, in principle, we are planning to take conventional power plants that burn fossil fuel, capture the carbon dioxide and water that they produce, and use photo-powered systems to convert CO2 emissions to methane or other carbon-based fuels, and kind of like a solar farm beside a conventional power plant. The methane comes from CO2 and water, which we get conveniently from the power plant as well. The methane produced can then be fed back into the plant. So in a very real sense, we are talking about solar powering conventional power plants with the kind of systems that we eventually see incorporated. A little more science: for this kind of system to happen, you need two types of electrodes. We are going to be looking at the cathode or the reduction side, and you can envision some sort of semiconductor attached to a chromophore or dye attached to the catalyst. The catalyst job is to electrochemically reduce CO2 to fuel. I've got methane here. Ideally, it could be diesel or anything. And the chromophore or the dye's job is to accept solar energy, to be excited by light, promote an electron, use it for reduction or oxidation, or use it, you could push the electron into the electrode and then get an electrode from the catalyst. In this case, you must excuse me, I've got I don't know if you can see my screen, but I've got a bunch of people in front of this side of the slide, so it's a little hard to see. Bear with me one second. No, I think we're just going to have to bear with it. That's okay. But so the catalyst job is to do the electrochemical reaction. In this case, I believe it's oxidation of water. It's covered by a list of speakers. Here we have the chromophore. Its job is to accept sunlight, promote an electron into an excited state, pump that electron into the electrode, and then extract electron from the catalyst as it's oxidizing water to oxygen. On the other side, we would have the reverse system. The chromophore would be excited, pump an electron into the catalyst, which would be used to reduce the CO2, and then get an electron from the cathode, which would be ultimately coming from the anode. So the whole idea is it's a closed system powered only by sunlight. If you think about it, plants do this already. All of the hydrocarbons that we are burning as fuel now originally was carbon dioxide in the atmosphere. Millions of years ago, cyanobactin and various other algae had converted that via photosynthesis into plant matter that was over millions of years compressed into oil and what have you. We already are solar powered, but of course, we want to do it much more quickly and prevent CO2 from going into the atmosphere. So the approach that we are looking at, this is the technical side of the slide talk, is we're looking at photoelectrochemical cells, where you have well-defined separate photosensitizers, well-defined electrocatalysts, and well-defined electrode compounds, semiconductors that we use to conduct electrons. And the academic advantages of these systems is you can divide them up and develop all three independently to work with each other, as opposed to making one catalyst and chromophore an electrode that does anything. Most of the molecular dyes that folks use are ruthenium and iridium compounds. They're very tunable. They do charge transfer and visible light. So they're very good for this, but of course they are ruthenium and iridium, and we've got to get away from that. And I'll show you how we do that in the second part of this presentation. So going to the conventional work now, you take ruthenium with these pyridyl compounds on them, BIPI, pyridine compounds, 2+ phosphonic acid linkages. The conventional approach is to react these linkages with a titanium dioxide surface. You get phosphonic ester bridges here. The other way to do it is to put carboxylate groups here. They react with the hydroxides on the surface of TiO2 to form ester linkages. So these have been used for years because they are very well defined. They have good photoactivity, but they have no stability to alkaline conditions at all, which is a huge limitation because ultimately we must make these systems abundant, and most abundant systems can't operate. Most abundant metals like iron and stuff like that cannot operate under acidic conditions where these operate. They need alkaline conditions. So that was the first problem that we addressed with our research. And our early approach was to kind of take this modular idea, this idea of molecular building blocks, and see if we can use it to systematically change all the components in the catalysts and dye to optimize them quickly and efficiently, because you have to try a lot of things to find something that works. Anybody who's a graduate student or a postdoctoral researcher in this area or any area knows that to discover a new system is very difficult, and it takes a lot of tries and a lot of failures until you get the system that works. And so we incorporated that into our building block model. So the way we started is we took phenanthroline, which is a common ligand with an amino group on it. You can purchase it through very well established chemistry. You convert it into the diazonium compound. These, again, this is pretty established chemistry for other groups. I'm not sure if it had been done with this. I think it had, but not to the kind of extent that we did it. These systems react electrochemically to kick off nitrogen. That's the driving force. Generate these radicals, and these radicals form bonds to the the electrode surfaces. In our initial studies, we used indium tin oxide, but it also works on carbon. Eventually, we do have to work with carbon as a source because it's inexpensive. Again, I don't know how much technical knowledge the audience has, so I'll go through this very briefly. This is a voltammogram where you've got the potential of the ITO, the amount of current that it's drawing versus potential. Standard calomel electrode is our reference. And the way we do these depositions is we sweep the potential down to -2. In the first sweep, you have a large negative current corresponding to forming a lot of this and depositing on the surface. We continue the sweeps, and as you put more of this on the surface, the current decreases because you're blocking sites for further growth. So this is a really convenient way to take various electrodes, we'll talk about titanium dioxide later, and put this coordinating ligand on it. Okay, I'm just going to take one more second. No, I cannot close that window. Okay. We are very careful about the work we do, and so we characterize these surfaces as much as we could. XPS showed us that the pyridine nitrogens were on the group. You can, on the surface afterwards, you can electrochemically reduce these by a known chemistry. to put a couple protons and electrons here by reducing down one of the pyridine rings. And we measure the charge for that reduction. You can see we go much lower in voltage here than we did during the deposition. So we didn't do any of that during the deposition. But here we crank the voltage. You can measure and count the number of electrons here, and it gives you an idea of the coverage. And you can see it's about 2.5 times 10 to the minus 10 moles per square centimeter on this system. We can also do an electrochemical measurement with ferrocene in solution, cyano iron, iron hexacyanide 3 minus and 4 minus in solution. This is the electrode without the coverage. This is afterwards, and you can see a lot of the sites are blocked, and you can learn something about you can investigate something about the properties of the film, which we won't go into today. But we have a pretty good idea. In fact, I think it's undeniable that we've made this, and we also know how much. So when you characterize the solid, have you made it? What's its state, and how much is on there? So in our mind, we can turn ITO, we can turn TiO2, carbon, into a classic ligand in transition metal chemistry. We then react, and this is bonded to the ITO by a carbon bond to the surface, probably an oxygen bond on the surface. I can't really imagine it being anything else. We then invented some chemistry where we took this iridium compound with a couple acetonitrile ligands and reacted this with this surface-bound ligand. And we made this iridium compound, which is the chromophore that folks use with iridium compounds. We made the ruthenium analog to make this compound. And you can see this chromophore with the two Bippy rings and the phenanthylene, let me pop it back here, is pretty much the same as this one or this one, only instead of having these groups, which are base sensitive, we now have a direct carbon oxygen bond here or carbon electrode bond. So it allows us to put any metal we want on here, and it gets around the problem of having that acid sensitive or sorry, base sensitive linker here, right? So did it work? Yeah, we think it did. This is the electrochemistry of the iridium compound. We start by sweeping up the voltage and then bringing it down. This peak here in the chromatogram is for oxidation of the iridium-3 to iridium-4. Count the number of electrons, and that tells you how many iridium centers are on the surface. And we get 2.8 times 10 to the minus 10, which is pretty close considering the accuracy of these numbers to how much phenanthylene we put on these electrodes. With the ruthenium compound, you can do the same thing, only the ruthenium is not that great a number because the compound decomposes when you take the ruthenium-2, in this case, up to ruthenium-3. But again, we get these numbers, 2.5 to 3 times 10 to the minus 10 moles per square centimeter. So everything is consistent, at least that we are making these components on the electrode surface. You always do controls. This is the ITO indium tin oxide with just the phenanthylene. You see it's got some peaks here. So you subtract that from these numbers. This is bare electrode. We cranked up the intensity here. This is a bit of technical details about how these measurements were done. A little more characterization, not too much. This is more of an activity talk than a characterization. We do XPS, which is kind of the standard X-ray photoelectron spectroscopy, which is a kind of standard surface characterization that we do. You can see the iridium peaks that show you that it's iridium 3+ as expected. You can also get the iridium to nitrogen ratio, which is 1:4, which is, let me go back here, as expected. You've got 4 nitrogens to 1 iridium. There are carbon iridium bonds here. For the ruthenium, you've got 6 nitrogens for 1 ruthenium. And indeed, the data show it comes through, which is nice. So when you characterize one of these compounds, you don't get one number that tells you everything. You have to find pieces to the puzzle and see if they fit. And the oxidation state of the ruthenium is as we expect it to be, 2+. We do UV-Vis. This is the model compound in solution. It's UV-Vis absorption spectrum in the solid state. You can see there's probably as close of a match as you're going to get with these systems. Here is the surface UV-Vis reflectance, I believe UV-Vis of the ruthenium compound, the model compound in solution. And you can see there's correlation, at least in the shapes. Estimating the coverage, we get about 2.8 times 10 to the minus 10. So there's that other measurement of the number in an independent way. So it's kind of confirming what we're doing. With the iridium, it's 3.1 times 10 to the minus 10. So this number correlates to some extent with this number, which we get from oxidizing up the ruthenium and iridium, which correlates to this number, which we get from reducing this down electrochemically. So we're pretty confident that we're making these. You can never prove anything, but we're pretty confident that we're making these. We also, to do a direct control, we always make electrodes in-house to have that one-to-one comparison. So we made the model compound and attached it to TiO2. And we've made our electrodes on TiO2 later, but I'll point out that when we do the coverage on TiO2, we found something pretty interesting and we think is relevant. If you look at the coverage of the known compound with UV-Vis, you get this number, 9 times 10 to the minus 9. We didn't expect the same number, but interestingly, if you do the measurement of the amount of ruthenium with electrochemistry, you get a smaller number. Okay, so this is 9 times 10 to the minus 9. This is 4 times 10 to the minus 10. And what we think is going on here is this deposition is indiscriminate. It puts ruthenium anywhere on the surface. This measures only the stuff that is electrochemically wired to the electrode. This is measuring all of the ruthenium on the surface. And so you can see that you get a lot more on the surface that is electrochemically wired. And whereas for the prior work, we had more of a correlation. So just to compare, looking at the ruthenium numbers only, I'll look at it all of them. Based on cyclic voltammetry, the amount of Fen was 0.24. These numbers are times 10 to the minus nanomoles times 10 to the minus 12. Iridium based on electrochemistry was 0.28, ruthenium 0.24. On TiO2, we did it there as well to have a higher surface area, 2.2 for iridium, for ruthenium, 2.0. For the control compound, which is put on by the phosphonate bridges, 0.4. So electrochemically, we're putting more sites down where the actual wire surfaces are on the electrode, and that's because of the nature of our deposition. UV-Vis, you can't do it for ITO Fen, it doesn't absorb there, but it's the numbers again pan out. But I'll just point out for the phosphonate deposition, you have much more iridium on the surface, ruthenium on the surface, okay, than electrochemically accessible. With our system, we have more that's electrochemically accessible and also higher, and we don't have, if you like, waste on the surface. We've also done some ICP-MS where you dissolve off everything in acid, measure the amount in surface in solution, and you can see that it's all kind of adding up and the numbers are reflecting the same trend. So what about activity? So the way you measure activity in, excuse me 1 second, please. Thank you. The way you measure activity in a photoelectrode is you set it to a certain voltage. In this case, we're minus 0.3 volts versus the standard calomel. you shine light on it of known wavelength and known intensity, and you measure the current that you generate. So what's happening in these dyes, why they're so popular, although I would grant too expensive, is when you shine visible light on the ruthenium at about 450, you promote an electron from the metal to the ligand. It's metal to ligand charge transfer that occurs in the visible range, and the charge separated system that you make has a long lifetime. In this case, the electrons injected into the TiO2, that's the charge we make, and we use triethylamine as a control, and it donates an electron into the ruthenium-3. So it's a continuous cycle. We're using triethylamine as a model. And again, you hit it with light at a known wavelength and you measure how much current the thing generates. This is TiO2 in the pink. This is under basic conditions, pH 12.6. There's the ruthenium phosphonate, and as I said, it's base sensitive and it falls off the solution instantly and gives you no activity whatsoever. This is TiO2 with just the ligand. You can see it's not doing much. This is TiO2 with our ruthenium compound, and it's converting the sunlight into electrochemical energy at a higher conversion than the literature compound or the controls under basic conditions. I'll also point out that ours is doing pretty well under these conditions with much less loading of ruthenium. Our ruthenium loading on this electrode is 2.2 times 10 to the 9. The stuff we put down with a conventional is 9 times 10 to the 9. So it's about 5 times or so, 4 times as much. And we're doing very well. Looking at the long-term oxidation, let me just orientate myself. So you turn on the light and then you just watch how the current changes at a given voltage. This is one sunlight simulation. If I am correct, no, it's 450 nanometers. And you turn on the light, you get current, and then you watch it decay. This is our ruthenium compound. This is the free ligand. This is TiO2 and the literature compound, the kind of gold standard for the literature. And you can see that it's decomposed and is not doing anything here. Under neutral conditions, now moving into the territory where the known compounds are more stable. These are the controls. We'll ignore those, but this is our compound, and you can see it's doing pretty well out here at the long wavelengths, which is important. The known compound is kicking in and beating us at around 450. But again, I'll point out it has about 4 times the loading as our compound. So we're doing okay, all things considered. Steady state under neutral conditions. To make a long story short, the literature compound gives more current per square centimeter than ours, but if you normalize it to the amount of catalyst, we're doing better than ours. And I think the amount of catalyst is a better number than geometric area. And if you look at the rate of decay after it's stabilized at about 200 seconds, if I understand this correctly, again, you have to forgive me, some of my stuff is being overlapped by Zoom placards and whatnot, but our stuff is here, again, more stable than the ruthenium stuff, even under neutral conditions. So it looks like we have a way to make these electrodes. Just to give you another quick thing that we're looking at, we put this compound on with the same kind of way. We put that ligand on first, then we put the ruthenium on. This ruthenium has a BIPI and a phenanthroline with 2 carbonyls. We condensed it with this compound to make carbon nitrogen double bonds here via condensation, elimination of water. We made a RURU compound. And so we view this as molecular Lego, where you can just add different components depending on which back you put it in. This is a bit of performance data, and the ruthenium dimer has better performance than the monomer. So that's good. So it shows it's heading in the right direction. But I think more importantly here is the fact that we've got this versatility where you can put the electrode in different solutions and put whatever combination of things you can. I will point this out quickly because we have no idea what's going on with this one. We came up with a bizarre result. We're still looking at this. This is a plot where we just held the voltage and shone light on it at different wavelengths. And in long wavelength visible light, we get a reductive current on top of the wave. At short wavelengths, it switches over and we get an oxidative current. We really have no idea why this is switching over. Perhaps here we are oxidizing the stuff, giving us the reductive current here, if you like. And perhaps up here we were reducing hydrogen protons to make hydrogen. Like I said, we really don't know, but we've never seen one switch before. So that's something interesting that we're going to have to look at. So once you build new stuff, you get new reactions and new things to learn, and hopefully new systems that are applicable. I want to change the topic just for a second. One of the great things about working in energy, one of the most important things about working with energy is public and school outreach. Everybody, even the folks who don't believe in climate change, are interested in hearing about climate change. And in all the research I've done, this one is uniquely this topic is uniquely suited, and it's great to go to classrooms and go to the public and talk about the research we're doing. And so I'm just taking a little break from all the technical stuff to show you the slides that we show students of any age, and they can understand and grasp what's going on and realize the importance of this problem and how maybe they should think about getting into it through communication, through art, through outreach, through talking to people, through perhaps even becoming scientists. They all want to learn about it. So this is one of our classroom presentations. What we're doing here, this was at Halloween, so some folks were dressed up. You can't see me, but I was dressed as a mad scientist, of course. We've got students here squeezing raspberry juice. This is a sock full of raspberry juice, and these folks are industriously squeezing it into a cup. You put a standard titanium electrode in it, shine a flashlight on it, the raspberry juice sticks to the TiO2, and you get a spike in current when you shine the light on it. And so the students of all ages, we've got them making raspberry juice solar cells. They love it, but it also gives them an idea of the research we're doing. So we've given these presentations over USA, Canada via Skype a Scientist, which is a good program. And of course, meeting students in person. COVID has interrupted with this, but now we're getting back into meeting folks in person. And I just want to show you the slides that we are showing to people in grade 3, grade 7, grade 10, and they're understanding what's going on and getting some good knowledge and hopefully inspiration out of this. And I encourage everybody to educate folks in this way. So I'm now going to give you slides that folks in grade 1 have received. Don't worry, there's no exam at the end of this talk, but it gives you an idea of what's going on. So we talk about where energy is from burning combustion, and how we need this energy and how it makes CO2 and water. We talk about solar energy to the students. They love hearing about it. This is a slide that one of my postdocs made. I think it's brilliant. And we talk about how plants use photosynthesis to do this already, and how our science project is to make an artificial leaf to do this. And this really engages the students. And of course, we have them squeeze raspberry juice and we have folks from all over the world doing this, which is phenomenal. Squeeze raspberry juice and try to make the solar cells themselves is very messy and very engaging, and I have to work really hard, and it's great for them. This is a slide I give them. This is the same slide I gave you in a different form. Okay, please don't be insulted. Like I said, this goes to everybody. And we talk about fossil fuel plants, CO2 capture. This is the kind of stuff that folks at any level get something out of, and it gets them thinking about their future and how we can change it. This is another slide where we talk about our catalyst. One of my students put a happy face on the dye here, which I think is excellent, what the catalyst is doing. And they get something out of this. And of course, they make it themselves. You can teach them what a catalyst is, all sorts of stuff. So, now back to our regularly scheduled program, but I wanted to put that in there to give everybody a break from all the technical stuff, but also to let you know this is a great topic for public outreach at all levels. Okay, so let's go back to some science. Iridium, ruthenium, you're not going to solve the energy crisis with that. You have to come up with a molecule that's inexpensive, effective, stable, a molecule that almost anybody can make without much infrastructure. Without it, we're not going to do anything, if you like, applicable. So we looked at these dicyanobenzene carbazole dyes. They absorb light in the near visible. And what you get is a charge transfer from the nitrogen to the dicyanobenzene, generating a cation and an anion pair. Getting a little technical, these systems form the singlet state. When they are excited, they undergo intersystem crossing to the triplet state. These are stable, and you can dump this electron into electrodes or into CO2. And we think we can use this positive charge to oxidize water. So these have been around for a little while, but they're very, very, very important right now. They've been used for a lot of organic reactions. I don't think anyone's used one in a photoelectrode yet. So where we started with this research, come on, computer. Again, it's got to be easy to make. So without spending too much time on this, we take this precursor, which you can buy, carbazole, which you can buy, deprotonate the carbazole with a bit of base, and you can exchange that fluoride, and that fluoride selectively to give you this with that synthetic avenue open here. We can then react it with a variety of different ligands. Here, we've reacted it with this carbazole to make this substituted dicyano polycarbazole chromophore. So this is replacing the ruthenium and iridium we did before. And in fact, here we've got that NH2 group that we can graft to the electrode crystal structure to show we made it. 90% yield, 90% yield. Pretty straightforward stuff. We electrografted this on carbon, ITO. We've put it on TiO2 as well, if memory serves, via this diazonium chemistry, same chemistry you saw before. But now we've got this organic dye in one step on the surface. Little characterization, cyclic voltammetry shows it's there. This is in solution. This is on the electrode. This is the key peak here. It's at minus 1.5 versus SE. That comes from dumping an electron into this dicyanobenzene ring. It's a beautiful, reversible, fast electrochemistry peak, and you can use it to determine how much you've got on it and to characterize it. This is the UV vis of the species in solution, the UV vis of the electrode. They are compatible. I'm not going to run you through all of that characterization, but XPS shows it's there and various other things that we've done to test it. Looking at the activity, this is the activity under alkaline conditions, and the activity is 3 times higher than the ruthenium dye I showed you before, which is one of our better dyes. So the activity is a lot better with these organic things. They're a lot easier to make. And so it is the way to go. With all respect to our prior research, we did use these as a photocatalyst. So this is the diazonium attached to ITO as a solid state photocatalyst. Here it is on carbon. Picture of just some carbon felt with this stuff on it. We take this trans olefin, hit it with light, and you can isomerize it to the cis olefin. So it's a heterogeneous photocatalyst for organic reactions as well as solar fuels reactions. I just want to point out this one, we get 12,000 turnovers, 80% conversion after 48 hours. And one of them, we get 87,000 turnovers by reusing it. So it's a really reusable photocatalyst for organic reactions. which is something we are pursuing. These reach photostationary state for the folks in the biz after 48 hours. So it's a good catalyst for things besides solar fuels. We can modify this group again by putting other ligands on, imidazoles, and then after we put the imidazole, this is an excellent site for coordinating catalysts. This is an excellent site for making NEC. We've made a lot of these. One example, we coordinated this to this manganese compound. We're writing this up right now. The imidazole sticks to the manganese to make this. This now is, although it's not a lot of turnovers, it is a purely organic dye, a purely abundant system. So we got rid of all the ruthenium, all the iridium. We're just using abundant stuff here. And we stuck this solution in a bath that only lets invisible light. It was one sunlight simulator put through a chromate bath to get rid of any blue light at all. And we get actually 60 turnovers out of this. So it's a purely organic system for a model CO2 reduction reaction to make carbon monoxide, which is a precursor to methane. I believe that's one of the first times that was done. So it's exciting in that way. Taking these compounds, we can deprotonate them to make the corresponding NHC and heterocyclic carbene. If you're in the business, you know that these ligands are very powerful activators for metals. And this is one of the only organic dyes with an NHC built in. Proton NMR before and after, that hydrogen is right there to show that it's gone. That is an impurity. I apologize.
Hello.
It works very well.
Okay.
Uh-oh. Long story short, this polymerizes very easily on electrode surfaces. So this system allows us to make a lot of different derivatives, put a lot of different metals on, and then we can polymerize it and put it on electrodes in one step. So I'll just leave the conclusion slide up here for a second. Long list of stuff that we've done. I want to thank my group, my students that did this research with me, the University of Alberta and Future Energy Systems and NSERC for funding this research. I'll go back to here and answer any questions. Sorry about going a bit long on that.
Thank you very much, Prof, for that detailed presentation. We are grateful. At this time, if you have any question or comment, you can raise your hand. Then I'll unmute you to ask your question. Hello.
Well, while folks are thinking, I just apologize for going a bit long, but I had to throw in those slides in the middle that we use to talk to public schools to let folks know that this topic is of a lot of interest for people on the at all levels.
Hello.
Hi.
Yes. Okay, Doc.
Yes.
Any comment for Prof?
Yes. I would like to find out from Prof. If aside chromophore, there are any other dyes that could be used for this process.
There are many dyes out there. Some people look at semiconductors. Bismuth vanadate is one. And so we're all taking different approaches to this project. The heterogeneous, or if you like, salt chromophores that people look at, bismuth vanadate is one. Perovskites are another. They are another way to do this. They all have their pluses and minuses. our system is pretty easy to do and defined, and it's environmentally benign. Their systems absorb at different wavelengths. I believe ultimately we're going to combine a bunch of chromophores. You've got ones that absorb at one wavelength, ones that absorb at another wavelength. If we want to be efficient, we really need to absorb all of the sunlight's energy. So, for example, really efficient solar cells like the kinds they put on Mars, they have different components that absorb at different ranges of the visible spectrum to cover it all, to be as efficient as possible. I believe that we're going to use a mixture of chromophores to do that as well in whatever the ultimate electrodes look like for these systems.
Okay, and I want to also find out if there was any study on impedance with regards to the research you are doing. Did you try looking at if there are any impedance that might affect the efficiency of the cells being developed?
That's a very good question. I can say that impedance is a big problem that we have to take into account. I didn't have much time to look at it, but the question is all about resistance to electron transfer when you're putting these plastic films on the electrode surfaces. And normally, as you build a thicker film, you increase the resistance or the impedance, and you shut the thing down. I didn't have any time to talk about it, but this polymer has, we discovered this almost by accident, but this polymer has been a blessing in many ways. It's based on carbazole, and when you oxidize up carbazole electrochemically, it becomes conducting. So we've done other studies blending this with polycarbazole, and what we find is at high voltages for water oxidation and stuff like that, impedance is not a problem because the polymer itself conducts charge, it conducts protons, and it conducts ions. So it does it all for you. It's remarkable stuff. So I'm really grateful for your question. I already went too long, but it is a big, big problem. If you coat your electrode with plastics or molecules, you're going to shut down how much charge. You can increase the impedance, or if you like, the resistance of the system. And it's something you always have to keep an eye on. But fortunately, carbazole gave us a solution to that, at least at high potentials where it is conducting and it doesn't seem to get in the way. I didn't talk about that work, but we've measured the impedance of those systems and it's remarkably small for water oxidation potentials. It's wonderful stuff.
Thank you for the answers.
Yes.
Yes, thank you for your question.
Yes. Thank you, Dr. Zaruk. I've seen that I've not seen any hand raised, and probably Prof, because it's a new field here, a lot of us haven't explored it. So this webinar is an introduction to most of our students to explore photosynthetic organic material as fuel cells. And we are grateful for this opportunity and then giving us this eye-opener to explore the options of renewable energy. But what I want to find out is, Prof, how about the commercialization? What are some of the things that one will have to look at if you want to commercialize this technology?
Boy, these questions are perfect. So the beginning of our talk was very meaning the folks that work with me on this, and I'm very grateful for all the hard work they did, and for Fez for being patient with us to start this. It was a new project for our group as well when we started it. If you're going to commercialize I touched on this topic. If you're going to solve the world's energy problems and climate problems, it can't be expensive. It must be easily scaled. You must be able to make it with pretty straightforward stuff. You can't have ultimate air sensitive chemistry with glove boxes and high vacuum depositions and whatnot. So the answer to your question is it's got to be cheap and easy and scalable. It has to be. And so the second half of our project is addressing that. We have a system that I didn't talk about that works really, really well. And we're just starting to talk to companies about this. And what I've learned with working with companies is you can't say to them, hi, here's a brand new idea. Stop everything you're doing and work on this. They'll say no. But what you can say to them is, our system is easily adaptable. Can it work with yours? Can we put it together? So it all goes back to this idea of being easy to adapt and scale and use. Otherwise, industry can't touch it. I hope that answers your question.
Yes, Prof. Thank you for that response. Yes. So I think we've exhausted our time, and I'll call on our Dr. Zaruk Abubakar to give the closing remark note. But before then, I would like us to switch on our cameras so that we see all those who are on, can see our faces. At least Prof has been speaking to virtual human beings for some time, so that he can see our faces.
I have to stop sharing for a second here to do that.
Yes.
There we go. Oh, wow.
I'm joining from
honored.
Turkey. I'm joining from Istanbul, Turkey.